Welcome back everyone to this series of lectures on distribution plots. In part 1, we're just going to work on understanding the different plot types and how they're constructed, so it's just slides and theory, and then in part 2 we'll actually code it out with Seaborn. So distribution plots display a single continuous feature and help visualize properties such as deviation and average values such as the mean. So there are 3 main distribution plot types and they all build off of each other. There's the RUG plot, the histogram, and then the KDE plot, which stands for kernel density estimation. So let's explore the distribution of those employee salaries that we've already seen. And one way to do this is just through a RUG plot. And a RUG plot is the simplest type of distribution plot, and all it does is it merely adds a single dash or tick line for every single value. So the y-axis doesn't actually really have a meaning for a RUG plot. So here we can see the RUG plot of all the salaries, and all this is doing is just at the very bottom, it adds a single blue line tick for every salary value. And in this case, the y-axis is kind of just meaningless. So optionally, you can adjust the height of the ticks to whatever height you want, really. But again, it's essentially just one tick per data point along an X salary range. And right now, this y-axis is not indicative of anything. And this is the RUG plot, the simplest way to show a distribution. So problems with the RUG plot is the y-axis is not really interpretable. And then we can see here that what is nice about the RUG plot is I immediately see some outliers. So if I wanted to know the highest salary or the lowest salary, I can see those single ticks quite clearly, such as the highest salary near $160,000. And I can also tell that many salaries are between $60,000 and $120,000. So I can see where a lot of ticks are. So clearly there's a mass of ticks right in the middle. However, so many ticks could be right on top of each other. I just can't really tell in this situation the way we've drawn it here. So what we're going to do is convert a RUG plot to a histogram, which is a little more interpretable and builds directly off the RUG plot. So what we're going to do is if we count how many ticks there are per various X ranges, we can create this histogram. So I can count how many ticks are there between 40,000 and 50,000, and then between 50,000 and 60,000, and so on for each $10,000 chunk. So what I want to first do is explore this very simple example. So here we have some continuous feature that goes from 0 to 30, and then we're going to place the RUG plot ticks. So overall, the entire data set only has 6 points. One of them is in between 0 and 10, 3 of them are in between 10 and 20, and then 2 of them are in between 20 and 30. So in order to build out the histogram, what we do is we first have to choose a number of bins. So the number of bins we want is just how many chunks are we going to cut up the x-axis into. So I'm going to say let's choose 3 bins since it makes sense because it divides everything in sizes of 10. So we'll go from 0 to 10 is one bin, and then 10 to 20 is the second bin, and then 20 to 30 is the third bin. And these bins should be the same size. So they're all from range of 10x units. And then what we're going to do is we're going to count the number of ticks that there are per bin. So there's 1 tick between 0 and 10, 3 between 10 and 20, and 2 between 20 and 30. And then we'll create a bar that is as high as the count. So essentially what we're going to do is for each of these bin widths, we count how many ticks there are, and then we create a bar that's as high as the count. So there is 1 tick between 0 and 10, so that means that bar gets to be 1 unit high. And then there are 3 bars between 10 and 20, or 3 instances, so that means that bar is 3 points high. And then between 20 and 30, there are 2 instances, so that bar is 2. And so eventually you get this, which is your histogram. And so clearly it's showing here that there are more points between 10 and 20 than any other range as far as these bins are concerned. And here if I wanted to know how many points are there between 10 and 20, I would check the height of my bar. So now I actually have an interpretable y-axis and I have a clearer visualization of the distribution. And this is the histogram. So the histogram is now complete. And what we can do is we can also normalize the y-axis as a percent if we wanted to. So sometimes people show it as the actual count, but don't be surprised if you see it like this, which is essentially a percentage of all the points. So here I can see that middle bar lines up with 0.5, meaning half of all the points in the dataset fall between 10 and 20. Now we can also change the number of bins to show more detail and variance instead of general trends. So it's a bit of a trade-off. Here we have a certain number of bins, but I could increase it to try to get a little more detail, or I could really increase it, but if you go too high in the bin count, there's going to be certain bins that are completely empty. Now Seaborn also allows us to add on what's known as a KDE plot curve or kernel density estimation plot on top of a histogram, which shows you what a continuous probability function would look like for this particular data set. So let's actually explore in a little more detail what this KDE plot is and how it's actually constructed. So KDE stands for kernel density estimation. And the way it gets that name is that it's a method, formally speaking, of estimating a probability density function of a random variable. And in simpler terms, all that really means is we're going to estimate a continuous probability curve for a finite data sample. If we look back at this histogram with the KDE plot on top of it, theoretically, we don't actually know every single point for every single salary as far as what's the probability of someone in a larger sample having a salary of, for instance, between 60,000 and 65,000, because we're dealing with a finite data set. So the probability curve here with the KDE, that blue line, it allows us to kind of behave as if we are dealing with a continuous probability curve, when in reality, we're really just dealing with discrete measurements of a finite data sample. So let's go ahead and construct this so we can actually see how this works. So I mentioned that KDE plots, they're really best understood by visualizing their construction. And we can do this by first starting off with a rug plot. So what we're going to do is just take a sample of some sort of continuous feature, and this feature can be negative or positive or both, doesn't really matter here. And here we have the rug plot for that feature. So it looks like more or less this feature is kind of centered around 0, but it looks like we have slightly more points on the positive side than the negative side. So what we're going to do is build out the kernel density estimation plot. And what we first have to do is decide on what kernel we're going to use. And the kernel is just another way of saying what probability distribution do you want to stack on top of each of these little ticks. And the most common one to use is the Gaussian distribution, otherwise known as a normal distribution. So you've probably seen a normal distribution curve before. What we're going to do here is just stack a little normal distribution on top of each of these rug tick points. So essentially, every tick point now has a Gaussian curve which is centered at that tick. So you'll notice that we have a lot of curves kind of towards the center near 0, and then a couple of curves on the outside. And then what we want to do is, in order to build up an overall curve, what we can do is actually we can just add these all up. And when you add up these curves, you're going to get something that looks like this. So at the end of the day, we end up with this kernel density estimation plot. And notice now we have this density, and essentially what it's telling you is the probability as if it was a continuous distribution. So now we have this curve that's completely continuous, and we were able to build it off a finite data set. It's another way of just showing you the distribution of a continuous feature. So clearly someone looking at this would say, oh, most of the points are probably between -2 and 2, which would be true. You should also notice that because of the way the kernel density estimation plot is constructed, there is the ability to go beyond, as far as the curve is concerned, the original data set. So notice here that our lowest value was -2. But because we centered that Gaussian distribution around -2, it's going to leak past -2 both on the left-hand side and the right-hand side. So that means when you're summing them all up to create this curve, you're actually going to get a probability for values less than -2, which may or may not be true depending on what data set you're actually working with. So it's not uncommon to actually do a hard cutoff at a certain spot in the kernel density estimation, and we'll actually show that later on. For example, when we're dealing with salaries and we were to draw a KDE, we're going to draw a hard line at 0 because no one has a negative salary. So other things you should note is that you can actually change the kernel. It doesn't have to be the Gaussian kernel. And you can also change the bandwidth. And the bandwidth used can actually make your KDE show more or less of the variance contained within the data. And what we're going to do is in the next lecture, we're going to explore how to create all these 3 plot types as well as the parameters that we can adjust with Python and Seaborn. So I will see you at the next lecture where we actually get hands-on and code this all out.